Okay, so it's my great pleasure to present today Andrei Rapinchuk from University of Virginia, who is actually speaking first time on our seminar in Brasilia. All right, and he is going to speak about groups with bounded generation, old and new.
Yes, thank you very much for the invitation, and in fact, for the opportunity to discuss one of my favorite topics, groups with bounded generation. So let's go straight to the definition. An abstract group gamma is said to have bounded generation property if one can find a finite collection of elements in it such that the group itself can be written as a product of the cyclic subgroups generated by those elements. This definition has an obvious profinite version. So a profinite group gamma has bounded generation in the profinite sense if there exist elements in that group such that gamma itself can be written as a product of the closures of the cyclic subgroup generated by those elements. Obviously, if we have bounded generation for a discrete group gamma, it implies bounded generation in the profinite sense for the profinite completion of gamma. But the question of whether the converse is true remained open for quite some time. But the results I'm going to discuss today actually imply that the profinite bounded generation does not imply discrete bounded generation. And in some sense, one can think of this as an indication that in some situation, the profinite bounded generation may be more useful and maybe even more natural than bounded generation itself. So I will come back to this point in the very end of the talk, but in the majority of the talk, I will talk only about bounded generation for discrete groups. What is worth pointing out is that while bounded generation and its profinite version are purely group theoretic properties, what we will see in this talk is that both positive and negative results on bounded generation have very strong number theoretic connection. Let's begin with some remarks and examples. First, obviously, every group with bounded generation is finitely generated. Conversely, every finitely generated abelian, or more generally nilpotent group, has bounded generation. Furthermore, according to a theorem of Maltsev, every solvable subgroup of G and Z is polycyclic and hence also has bounded generation. Now, it turns out that in all other known cases, verification of bounded generation is non-trivial and, like I said, uses number theory. I must say that the first examples of sort of semi-simple groups with bounded generation appeared even before the formal definition was given, as a consequence of investigation of the following linear algebra question. So everybody knows that given a matrix with determinant 1 over a field, using Gaussian elimination, one can always reduce it to the identity matrix by a sequence of elementary row and or column operations, which results, of course, in the representation of this matrix A as a product of elementary matrices. What is important here is that if we implement Gaussian elimination, the number of steps required is bounded by a constant of the magnitude n squared plus change. But what is important for us is that this constant is actually independent of the matrix A itself. Well, one can ask a very similar question for unimodular matrices over Z. Again, it's well known that every such matrix can also be reduced to the identity by using only integral elementary operations, which again results in a factorization where the entries of the elementary matrices are integers. So again, one can ask a similar question. Can this number of factors be bounded by a constant independent of A? So, and the answer should not surprise you. The answer is actually no, for matrices of size 2 by 2. And the group theoretic reason for that is that the group SL2Z is actually virtually free. Okay, but what about the case where n is 3 or larger? This question was asked by Dennis and van der Kallen in 1979 over any ring O of algebraic integers. And in fact, soon after it was asked, it was really answered by the following theorem of Carter and Keller, published in 1983. It says that if O is a ring of algebraic integers and n is at least 3, then every unimodular matrix over O is a product of a bounded number of elementary matrices. So this number is certainly independent of the matrix, but is mildly dependent on the field, or rather on the discriminant of the field. And I will come back to this point later. What I want to point out is that the result of the theorem actually gives us a factorization of the group SL and O required in the property of bounded generation, where all elements gamma I are unipotent. While the case of SL to O turned out to be a bit tougher, so in fact it was completely resolved only recently. As I said earlier, if O is Z, or in fact also the ring of integers in an imaginary quadratic field, then gamma fails to have bounded generation. In the case of Z, like we said before, SL to Z is virtually free as far as SL2 over the ring of integers of an imaginary quadratic field is concerned. So it's known that a finite index subgroup of gamma has a non-abelian free quotient, again, which prevents this group from having bounded generation. So all other cases were covered in the following theorem that we proved in joint work with my student Alexander Morgan and Suri. So in all other cases, the group of units of the ring is infinite. And if this is the case, then we prove that every matrix in SL2O is a product of at most 9 elementaries. And in this case, this result applies not only to the rings of integers, but also to the rings of S integers. Now, this result actually has a history of its own. So the first result along these lines was pointed out by Cook and Weinberger in 1975. They observed that this assertion can be derived from some results on the Artin primitive root conjecture, which in turn required the generalized Riemann hypothesis, which still remains unproven. Sometime later, Dave Morris reworked the preprint of Carter and Keller and Page to prove the existence of a bound using model theory. Well, in addition to some non-trivial model theory, he used a strong version of Vinogradov's result on Goldbach conjecture, that every sufficiently large integer can be written as a sum of odd integer can be written as a sum of 3 primes. And this argument gave really no bound on the number of elementary it takes to write every matrix in SL2O. Maxim Semirnov in 2014 proved the assertion for the ring Z localized with respect to P, using some results of his Brown, again on the primitive Artin's primitive root conjecture. So in some sense, that was a return to the original idea of Cook and Weinberger, but this time it was already unconditional. So in contrast, so our proof relies only on the traditional algebraic number theory, namely on Chebotarev's density theorem and some calculations with the power residue symbols. Of course, there is also some work on SL2, which is not mentioned on the slide. So I should say that for some fields, the assertion was proved by Leal, although these fields do not include the field of rational numbers. Then there was also the work of Kumar Murthy that proved the assertion if you localize sufficiently many primes. Okay. Also, there was a follow-up work by Bruce Jordan, where the number of factors required was reduced from 9 to 7 in some cases. In fact, this was done in all cases by my student Morgan, and Bruce and his co-authors also indicated some applications of this result. Okay, but what's important for us is that this theorem for SL2 yields a factorization for the group SL2O, where some elements are unipotent and some semi-simple, in other words, diagonalizable or even diagonal, with unipotent elements, or at least non-semi-simple elements all necessarily present. Okay. Now, in fact, bounded generation is known for many other S-arithmetic subgroups of isotropic simple algebraic groups over number fields. In particular, in 1990, Tavgin proved bounded generation for all Chevalier groups of rank greater than 1, and also for many quasi-split groups, with the group SU to 1 being a notable exception. Now, in my joint work with my student Igor Yarovenko, we considered also isotropic, but not necessarily split or quasi-split orthogonal groups. And my other student, Andrea Hild, also was able to consider some unitary groups. So there has been some activity in that area, which would result in new examples of groups with bounded generation every now and then. But why are we interested in groups with bounded generation after all? It turns out that groups with bounded generation have quite remarkable properties. So, and I would like to mention two of them, namely SS rigidity and the congruent subgroup problem, and briefly mention some others. So first, let's talk about SS rigidity. A group gamma is said to be SS rigid if it has finitely many equivalence classes of completely reducible representations in every dimension. So I'm talking about only complex representations now.
SS rigid means super rigid?
No, it's semi-simple rigidity, because what I'm saying here is that I'm considering only completely reducible representations. So, as a matter of fact, SS rigid groups may have infinite families of representations if you allow also some non-completely reducible representations. So at this point, we're talking only about completely reducible representations. And another way to think about those groups is to, first of all, if gamma is finitely generated, one can define the so-called character variety, which precisely classifies the equivalence classes of completely reducible representations. And then the group gamma is SS rigid if the dimension of the character variety is actually 0 for all m. Now, most examples of such groups come actually, as Pavel pointed out, from superrigidity results, namely from Margulis's superrigidity theorem. But some time ago, I proved the following abstract version that states that if gamma has bounded generation and satisfies the following condition, which Hyman-Best coined FAB, that says that every finite index subgroup has finite abelianization, then gamma is SS rigid. So let me point out that, of course, without assuming FAB, gamma cannot be SS rigid, because if gamma is finitely generated and fails to satisfy this condition, that a finite index subgroup can be mapped onto Z, which of course is not rigid. Another point is that while I stated this result for requiring bounded generation for gamma as a discrete group, in fact, if it remains valid if we replace discrete bounded generation with profinite bounded generation for the profinite completion. Are there any questions? So another property that I would like to discuss has to do with the congruent subgroup problem. Here is a standard setup. So let's consider an algebraic subgroup G of GLN defined over some algebraic number field. Well, it's okay to think about G as just being, let's say, SLN or the orthogonal group or something like that. Next, we fix a set of places S of the field K that contains all Archimedean ones. For example, if K equals Q, let's take for S the two-element set consisting of the infinite place and the p-adic place corresponding to your favorite prime P. Then in this case, the ring of S integers will be just Z localized with respect to 1 over P. Okay. In general, I will denote the ring of S integers by O sub S. And finally, we consider the group of points of algebraic group G over that ring OS. What this means is that I'm simply looking at all matrices with entries in OS that satisfy the defining relations for G. Again, if G is like SLN and OS is Z of 1 over P, then we're looking at the group SLN over the ring Z localized with respect to P. Okay? Furthermore, we let gamma hat denote the completion of gamma for the topology defined by all finite index normal subgroups. So it's just the profinite completion. On the other hand, so we let gamma bar denote the completion of gamma for the topology defined by the congruent subgroups. So when we have a linear group over a ring, then for every ideal of the ring, we can construct a natural subgroup, which is called the congruent subgroup. It consists of matrices that are congruent to the identity matrix modulo of this ideal. In the number theoretic situation, so, and therefore every congruent subgroup is really a normal subgroup of finite index. And then so we let gamma bar denote the completion of gamma for the topology defined by all these congruent subgroups. Okay. Now, the first topology is strong topology. So we have a natural map for the completions. And the kernel of this map is called the congruence kernel, denoted C. It is easy to see that C is trivial if and only if every normal subgroup of finite index contains some congruent subgroup. And this is the expected answer to the congruent subgroup problem in the classical situation. In fact, C is not always is not always trivial, but in any case, its size characterizes the deviation from the positive answer to the congruent subgroup problem. So now, by the congruent subgroup problem, we really mean the problem of computing C. And we're particularly interested to know when the congruence kernel is finite. Are there any questions about the setup? If no, then let's go to the statement of the theorem that relates this to bounded generation. So let G be a simple. I also need to assume simply connected, but let's not worry about this. Now then I need to make some technical assumption, and you don't really need to pay attention to this. because the Margulis-Platonov conjecture, which is mentioned in this statement, is actually almost a theorem now. But the important part is that the congruence kernel is finite if and only if the profinite completion gamma has generated if that's so we really thought about this as a possible uniform approach to the congruence subgroup problem, because at that time there was information coming from Fritz Grunewald that he was able to use the computer to verify bounded generation for some quaternionic groups, where in fact the congruent subgroup problem was and still remains open. I'll get to this point later. Let me mention some other uses of bounded generation. So in their paper published in 2013, Shalom and Willis used bounded generation to prove another conjecture, which is known as Margulis-Zimmer conjecture, in some cases where bounded generation was known. Bounded generation was also used to estimate Kazhdan constants for subgroups, including SLM. And to make this list sort of complete, let me also mention that the bounded generation in the profinite sense for pro-P groups precisely characterizes analytic pro-P groups. Okay, so this does show that bounded generation has some implications and applications, and so the available results actually create the expectation that all higher rank lattices in Lie groups should have bounded generation. So let me also mention that, as Fujiwara observed, that rank 1 lattices never have bounded generation. So this dichotomy between rank 1 and higher rank lattices is what you always expect in the theory of discrete subgroups. But the interesting part, change here is that as far as bounded generation is concerned, there is also this dichotomy or borderline between non-uniform and uniform cases. So let me explain what this means. So people have been interested in bounded generation for over 30 years, but we were not able to find a single example of an S-arithmetic subgroup of a simple anisotropic group that would have bounded generation. Well, let me just recall that we say that the group is anisotropic over a field of characteristic 0 if the group of k-rational points does not contain any unipotence. Examples of such groups can be found using division algebras. For example, we can take a quaternion algebra over Q and take the group which is defined as a group of norm 1 elements in the quaternion algebra. Then, since we're looking at the division algebra, there are no unipotent elements inside that group. That's a simple example of a group which is anisotropic, that is, does not contain any unipotent elements. Another example can be obtained that if you take an isotropic quadratic form, for example, take the sum of squares, then the corresponding orthogonal group does not contain any unipotent elements. So that's yet another example of an isotropic algebraic group. And well, the fact that we were not able to find any examples of boundedly generated arithmetic subgroups of such anisotropic groups led us to the following question. Well, question A, can bounded generation possibly hold for an infinite S-arithmetic subgroup of any anisotropic simple algebraic group? So quite a few people have been thinking about it.
Here above, bounded generation is missing. Over more than 30 years, no example of S-arithmetic.
Yeah. So I need to say that bounded generation is missing. Yeah, you're right. that's a typo, but the question remains.
Sure.
Okay. Now you can approach this question from a different perspective. As I told you that when we looked at, for example, SLNZ, where n is at least 3, then the bounded generation presentation for that group was involving only unipotent elements. When I switched to SL2, I told you that the bounded generation representation for that group involves some unipotent and some semi-simple elements. Okay. So one can ask the following question. Can you boundedly generate a group using only semi-simple, in other words, diagonalizable elements? Or more precisely, which linear groups are boundedly generated by semi-simple elements? Well, we were able to answer this question in a recent work, joint work with Pietro Corvaja, Jean-Bo Ren, and Umberto Zannier. So we have the following theorem, which I refer to as the main theorem of this talk. It states the following. So suppose we have a linear group, gamma, over a field K of characteristic 0. Now assume that this group is not virtually solvable. Then any possible presentation of bounded generation for gamma involves at least 2 non-semi-simple elements. In particular, a linear group which is boundedly generated by semi-simple elements must be virtually solvable. I must say that this is not a criterion. In fact, there are solvable finitely generated linear groups without bounded generation. But if we can make it into a criterion, if we limit ourselves to so-called anisotropic groups. So in other words, building on the definitions that I gave you for algebraic groups, let's say that a group gamma is anisotropic if it consists only of semi-simple elements. Okay, and then I have the following corollary of the main theorem, which is a criterion. And an isotropic linear group gamma has bounded generation even only if it is finitely generated and virtually abelian. And in particular, infinite S-arithmetic subgroups of simple anisotropic algebraic groups do not have bounded generation. Okay, this basically concludes the survey part of my talk. And after answering questions, if there are any, I'll show you some proofs. Are there any questions?
Well, possibly my questions I better ask after the talk.
Okay. So now let me walk you through the proof that SL and Z has bounded generation. First, it's an elementary statement that uses only Euclid's algorithm that any matrix over Z can be reduced to the following log diagonal form by a bounded number of elementary operations. So it's easier and uses only Euclid's algorithm. So in order to prove bounded generation, it is enough to show that any matrix of this shape can be reduced to the identity matrix inside SL3Z by a bounded number of elementary operations. And here I do not write the second row because the fact that this matrix can be written as a bounded product depends only on the first row. So in other words, no matter what second row you put in, these two matrices will differ by a single elementary transformation. And this has to do with famous many-key symbols that were instrumental in the initial work on the congruent subgroup problem. And in fact, the crucial property for the argument is the so-called bounded multiplicativity of many-key symbols. What it means in practice is that if we have any block diagonal matrix as above, then for any integer L, one can pass from the L's power of that matrix the matrix of this shape by 16 elementary operations. Okay, the point here is that the number of operations required does not depend on L. And this is verified by basically a direct computation, which is not trivial, but quite explicit. Now, on the next slide, I show you the effect of one elementary operation. You see, we do one elementary operation, and here in the right upper corner, we have an arithmetic progression. And of course, A and B are relatively prime because the matrix is supposed to have determinant 1. So using Dirichlet's prime number theorem, we can make B a prime number by a single elementary operation. Okay, so let's assume that B is a prime. Now, if we apply Dirichlet's theorem actually twice in a clever way, we can actually assume that both B and C are prime numbers, in fact, all prime numbers, P and Q, subject to the following conditions. So the GCD of these numbers is 1. This is achieved by using, of course, the Chinese remainder theorem and some elementary number theory computations, and eventually we use Dirichlet's theorem. So we can assume from the start that our matrix has this form where P and Q are odd primes subject to this condition. Okay, if so, then of course we can find integers m and n so that the linear combination of these numbers is plus or minus 1. And then let me call the first number S and the second number T. So what's the deal here? The deal is that, of course, by Fermat's-Little theorem, U, the 1, entry, raised to the S power will be plus or minus 1 mod P. So we can play the following game. We take the S power of our matrix, and by bounded multiplicativity, we can use 16 elementary operations to put your matrix in this form. Then the left upper corner becomes plus or minus 1, and then using simple elimination, you can reduce this matrix to the identity matrix by very few, I guess 5 elementary transformations. Okay. Now we can take also the transpose, use the same argument to find if its inverse is also a bounded product of elementaries. That's basically the argument. Okay. But still there are some mysteries about bounded generation for SL even 3Z. So now we know that we can decompose any matrix A as a product of a bounded number of elementaries. But what about the size of the entries in those elementaries? For example, if we know that the entries of the given matrix A are bounded by some constant m, is it possible to give a reasonable bound for the entries of the elementary matrices? So this proof doesn't give a nice or at least polynomial bound. Okay. That's the question that remains open. Also, I gave you this argument, and it looks like all you basically need to use is Euclid's algorithm. Well, but that's not exactly right. So in 1980, Van der Kaan showed that if we replace Z with C box X polynomials over C in one variable, then there is no bound such that every matrix is a product of n elementaries. Now, Van der Kaan's argument uses the fact that C actually has infinite transcendence degree over Q. He uses this to conclude that in K2 group of C, there are arbitrarily large or long products of symbols. So the question about what happens over Q box X or Z box X still remains open. Okay. Are there any questions? Next, I would like to show you a sketch of the proof of the main theorem. So let me recall that the main theorem tells us, so let me show you maybe this slide. The main theorem says that if we have a linear group which is not virtually solvable, then any possible presentation of bounded generation for gamma must involve at least two non-semi-simple elements. So in particular, and this is really the case I'm going to focus today, is that a linear group which is boundedly generated by semi-simple elements must be virtually solvable. So this is the main theorem. And now let me point out something that goes into the proof. So first we make two reductions. One is that in the statement we allow K to be any field of characteristic 0. Now there is a specialization argument that shows that it is enough to consider the case where K is a number field. In other words, we can assume that gamma is contained in GLN Q bar. The way we prove this is we show that if there is a counterexample over K, then there must be a counterexample also over Q bar. And the second reduction, I will use it only once, and I will tell you exactly where I need to use it. So assuming that gamma is not virtually solvable, we can do the following. We can take its Zariski closure, and then we can take what is known as the radical of the Zariski closure and divide the Zariski closure by the radical. So this reduces us to the case where the connected component of the Zariski closure is a non-trivial semi-simple group. Again, I will get to this later, but in fact, the key statement that I would like to share with you is quite elementary and uses only eigenvalues of elements. So suppose we have a matrix, gamma, then by lambda of gamma, I will denote the subgroup of Q bar, multiplicative group, generated by all eigenvalues of gamma. Okay, and then we have the following key statement. So suppose we have a bunch of elements in GLN Q bar. We assume that they are all semi-simple with one possible exception. And let gamma be another semi-simple matrix. Now assume that gamma has an eigenvalue, which I will denote by lambda, which is not a root of unity, and which satisfies the following condition. So the cyclic group generated by lambda is disjoint from the group generated by the eigenvalues of all other elements. And under this condition, we have the following conclusion. Then the intersection of the cyclic group generated by gamma itself with the product of the cyclic groups generated by the given elements, gamma 1 through gamma r, is finite. And in particular, gamma, the cyclic group generated by gamma is not a subset of the product of other cyclic groups. So it's to be useful not only for bounded generation, but in for other problems dealing with linear groups. That's our hope. Now, then to complete the proof of the main theorem, we need to show that given any finite collection of elements, gamma 1 through gamma r in gamma, we can always find another element of infinite order so that their eigenvalues are disjoint, or let's say independent, meaning that the subgroup generated by the eigenvalues of gamma has the trivial intersection with the subgroup generated by the eigenvalues of all other elements. But the existence of such an element follows from our theorem with Prasad, we proved in 2003, that gives the existence of so-called generic elements in the Zariski dense subgroups. Now, what I want to point out is that the proof of the key statement depends on the following very important result in Diophantine approximations. It's called Laurents Theory. So the statement is the following. Suppose we take the product of n copies of the multiplicative group of Q bar, and suppose omega is a finitely generated subgroup of that product. Now, suppose sigma is an arbitrary subset of omega. This theorem describes the Zariski closure of sigma. So it says that the Zariski closure of sigma is a finite union of translates of algebraic subgroup of what we call torus T. Now, and these subgroups are all given by characters. So basically what this theorem tells us that if there is a polynomial relation that holds on sigma, then this relation can be derived from relations of multiplicative type, which is given by characters, which also hold on sigma. And since I'm almost out of time, so let me just do the case where all the elements are just semi-simple. Since they are semi-simple, we can go ahead and diagonalize them. So we can find matrices so that after conjugation, our matrices become diagonal. So what we do next is we replace these eigenvalues with variables. So we introduce r times n variables, x11 through xrn, and take the following generic product. So, and we let p be the 1-1 entry of that product. So in other words, when you plug in lambdas or their powers, you'll be getting elements from the product of the cyclic subgroup generated by gamma 1 through gamma r. That's the idea. So we have this polynomial. Now let G denote the set of integers m, so that gamma to the m is in the product of the given cyclic subgroups. So this means that again, for each m in G, we can find integers so that the following holds. And as I explained to you, the construction of the polynomial P. So this means that we have the following polynomial relation. Okay. Then, so by construction, this polynomial entity holds on the following subset of sigma of the appropriate finitely generated subgroup. Okay. So we can use, we're in a position to use Laurents, and using the description of the Zariski closure provided by Laurents theorem, we obtain that some power of lambda is actually contained in the product of the subgroup generated by the eigenvalues of gamma 1 through gamma r, thus providing a contradiction with the independence of the eigenvalues. So that's basically the proof. Okay. Now, our theory implies that anisotropic S-arithmetic subgroups of anisotropic groups can never have bounded generation. On the other hand, there are many examples of arithmetic subgroups of anisotropic groups which are known to have the congruent subgroup property. So, and each example of this kind provides an example of a finitely generated group for which gamma hat, the profinite completion, satisfies bounded generation as a profinite group, but the group itself fails to have bounded generation as a discrete group. Now, in the remaining couple of minutes, let me just discuss where do we go from there. So, in other words, our main theorem shows that there are many groups, many linear groups, and many arithmetic groups that cannot possibly have bounded generation. So, should we just forget about bounded generation forever? Well, I don't think so, because the techniques that were developed to derive consequences of bounded generation can work with much, much weaker conditions. And so let me mention some of these conditions to you. One condition is, of course, bounded generation in the profinite sense, but there are still weaker conditions. So for a group gamma, let us denote by gamma n the normal subgroup generated by the nth powers of its elements. So, and then I can state the polynomial index growth condition. So we say that gamma satisfies the polynomial index growth condition if the orders of this quotient are bounded by a polynomial in terms of n. Okay. In fact, we still have a weaker condition, which I denote PG prime. So where we don't consider all n, but only n of the form number times a prime power. Okay. And the point is that these conditions are sufficient to derive, for example, SS rigidity and the congruent subgroup problem. So why are they better? So as I showed you, the verification of bounded generation for cell n is not quite a trivial matter. On the other hand, one can verify PG prime rather easily by quite simple computation with commutators. So in particular, we don't need any number-theoretic results. At the same time, one can obviously try to analyze PG prime by using some computer-based experiments. So the problem now shifts to the following. We would like to show that if gamma is a higher rank S-arithmetic subgroup of a simple algebraic group, then gamma satisfies PG prime. Another problem deals with amalgam. So if we take the group gamma SL2 Z of 1 over P, then this group can be written as a non-trivial amalgamated product of two copies of SL2, which of course is a virtually free group, over a common subgroup of finite index. And we know that this group has bounded generation. Now, you could also look at a sort of an anisotropic cousin of that group. So namely, we can take the algebra of quaternions, take the corresponding SL1 group of quaternions with no 1, and allow our quaternions to have only two primes, P and Q, as denominators. That's going to be my group. Well, this group is anisotropic, and while it does have a similar presentation as an amalgamated product, so it doesn't have bounded generation. So the question is, what's going on? So let me state problem 2. It's of course rather vague, but let me do it anyway. So to give a verifiable condition for amalgamated products of this form to satisfy bounded generation or to satisfy PG prime. Now, I must say that Grigorchuk and independently Fujiwara gave some necessary conditions for amalgamated products and other free constructions to have bounded generation, but these conditions do not apply, for example, to quaternionic groups. And again, let me finish this talk with the following rather vague general question. So I must say that all examples of semi-simple linear groups with bounded generation involve S-arithmetic groups in a very essential way. So the question is whether it's indeed true that all examples are in this way or another related to S-arithmetic subgroups. And particularly would like to know this for linear groups that are non-trivial amalgamated products. And that's all I have for you today. Thank you for your attention.
Thank you very much. Let's try to switch on microphone and thank the speaker.
Thank you.
And I open questions. Anybody has a question? Please unmute your microphone and ask.
I have a question.
Sure.
Yeah. So you prove that an azotropic linear group cannot be presented as a product of bounded number of cyclic groups. And
Yeah, that's
about
correct.
abelian groups, okay, finitely generated. if we start with finitely generated, what about abelian groups?
You mean abelian groups which are not finitely generated?
No, it's we start with finitely generated, which is not virtually solvable. No, okay, like do you?
But if you can write as a product of abelian groups, each of which is finitely generated, you get a product of cyclic groups.
Finitely generated. Yeah, you are right. Of course. Yeah. So I was thinking about, is it any generalization in characteristic P? Can you? Yeah. So.
Well, the thing is that there are very few boundedly generated groups in characteristic P. The thing is that if you have one, then it's you can make it P residually finite, and then you take the provided pro-P completion. It will be an analytic group, analytic in characteristic 0.
I see.
So for that reason, I mean, in characteristic P, you really need to consider other conditions than really bounded generation.
I see. Okay. Thank you.
Any other questions? Okay, I have maybe half question, half comment, because you already commented on this. So actually, for congruent subgroup problem, what is needed actually is a bound generation of the profinite completion, right?
That's correct. Yeah. All right. And even PG prime will do the job.
All right. And but for profinite completion, for example, there is no really methods to show bound generation. At least I don't know. Maybe you know any methods how for profinite group to check bound generation. I mean, for pro-P case, you mentioned that it is analytic pro-P, and this can be somehow sorted out. But for profinite group, I think, I mean, do you know any methods how to check it?
Well, one method is what we use with Yarovenko. So you could take, for example, an orthogonal group and write it as a product of orthogonal groups of smaller rank. Like if you have, for example, SLN, you write it as a product of SLN's M's, where M is smaller. Okay, but then somehow you need to show that the closure of SLM in the provided completion of SLN has bounded generation as a profinite group. I mean, there are certain techniques coming from the congruent subgroup problem, but we still don't have any solid argument.
Yeah, because
I mean, I don't.
In principle,
yeah, this doesn't answer your question, but.
No, because you see, you can start with arithmetic group, but if you don't have a congruent subgroup problem before, right? In the profinite completion, you don't have linearity or assumption, right? And so you cannot use.
No, you need to prove not exactly the congruent subgroup property, but something smaller. So you take a smaller group inside a bigger group, and then take the closure of that smaller group in the profinite completion of the bigger group. So you don't need to prove bounded generation for the bigger group, but only for the smaller group inside the bigger group.
I see.
That's not an argument. So that's only some kind of, idea. I don't know how it's going to work, but. So in other words, so in certain cases, you have bounded presentations of your group, algebraic group, as a product of groups of smaller rank. Okay, like you have an orthogonal group, you can write it as a product of 3 or 4 copies of other orthogonal groups of dimension 1 less.
But this way you're still using that actually your groups are linear. So if you take the abstract question how to prove for profinite group, how to check bound generation, it is not clear then.
No, I'm only talking about certain possible techniques for S-arithmetic subgroups.
I see.
Sorry, Andrei, can I come back to my question? Maybe
sure.
So you said if you have bounded generation by abelian subgroups, you also have by bounded generation for cyclic subgroups?
No, if abelian groups are finitely generated.
I don't see it really.
But if your abelian groups are finitely generated.
No, not abelian group. The group. Sorry. So I explained so the group is finite. So if you start with finitely generated group, and you ask finitely generated azeotropic group. And my
Yeah.
question was, is there any example that it can be represented as a product of finite number of abelian subgroups?
Which are not finitely generated.
Yeah, of course, yes.
No, this I don't know. This I don't know.
So, and this would be a generalization to mod P case, I think.
That's right. And maybe this property would also be enough. I need to see to derive congruent subgroup property and so on. But another, for example, boundedly property is that, you know, you take an element and you take the normal subgroup generated by this element, whether every element is a product of finitely many conjugates, of a bounded number of conjugates. That's another boundedness property that I think implies the congruent subgroup property, but I don't know how to check it. But PG prime seems to be the most promising thing that I can think about at this moment.
Another question, I mean, if since a pro P completion, or almost say pro P completion is much easier to check whether it is bound generation, right? Maybe one can go this way, or it is.
Yeah, we can talk about this. There are certain conditions that allow you to prove, and I can check it using Fritz computations, that certain pro P completions of certain quaternionic groups are p-adic analytic. That's a very sort of weak version. This can be checked.
Mm-hmm.
But not beyond that.
I see. Right.
We can talk about this more, so I need to get to my papers. But analyticity, I mean, can be checked.
Mm-hmm. Well, any more questions? If not, I'll thank speaker again.
Thank you for your attention. Thank you.